Hello everyone, I hope you're doing well. In this video, we'll be solving problem 2 from chapter 4 of Introduction to Statistical Mechanics by Roger Paule. Let's see the problem statement and we'll dive directly into the solution. So here's the statement. It says that an isolated macroscopic system at temperature 300 Kelvin absorbs a photon from the visible part of the spectrum, say lambda equals 500 nanometer. So that's the wavelength of the photon that has been absorbed by this macroscopic system. So this wavelength will help us to find out what amount of energy has been absorbed, because it is equals to the energy of photon. So that's a crucial information. Obtain a value for the relative increase delta W by W in the number of accessible states of the system. So we are given with temperature, we are given with lambda, and we have to calculate delta W by W, or relative increase in the number of accessible states. So that is something that we have to calculate. Let's see how we can do that and start the solution. We'll start with data and the temperature of the system. Let the temperature of the system is T, and that is equals to 300 Kelvin. Since there is only one system here, so we'll not be writing T1, T2 or T3. We'll just simply use T. And we have a photon whose lambda is given, and lambda equals 500 nanometer. And we can convert it into meters. Nano is 10 to the power minus 9. So it's this lambda is equals to this. And we need to calculate the relative increase in accessible states. Okay, we have to calculate the relative increase. So let's get into the solution part. We know that entropy is given by entropy change. Okay, entropy change is given by following formula: delta S equals Q by T. Here Q is the energy absorbed or released, and since in our case we can see that the system has absorbed a photon and it has absorbed energy, so there will be increase in entropy and it will be positive, and that Q would be equals to the energy of photon. So we can make it equal to E by T, where E is the energy of photon, and we know that energy of photon is given by Planck's formula. E is equals to hf. H is Planck's constant and f is the frequency. Since we are given with lambda, so we can convert this formula into lambda form. And since we know this formula, C is equals to lambda f, this is the formula for the electromagnetic waves that connects the frequency lambda and speed. So we can find out the value of f, and for that purpose we'll take lambda to the other side of equation. It's multiplying here, it will be divided here, so C by lambda would be equals to f, and we can insert this value right back into this equation. So instead of f, we'll write C by lambda. So at C by lambda is the energy of photon that we can insert right here at C by lambda, and T is already there. So that's the entropy change so far. We can call it as equation number 1. Now from Boltzmann hypothesis, from Boltzmann definition of entropy change, we can write that delta S is equals to KB natural log of delta W by W. That gives us the relative increase or decrease, whatever, in entropy. Okay, so we need to calculate delta W by W. Okay, and we know that KB is the Boltzmann constant. That's not a problem at all. We just need to know delta S, and we have this delta S. We can put this value of delta S right back into this equation to separate delta W by W. Okay, so we can do that here. We can put the value of delta S. We can write from 1. Delta S is at C by lambda T equals KB natural log of delta W by W. This KB can be brought to this side of equation. So we have this, and we can write natural log of delta W by W, that is equals to this on this side of equation. So HC by lambda KBT. Now the next step is to insert all of these values into this equation to evaluate what this is, and then we can remove natural log afterwards to get the value of delta W by W. Okay, so let's calculate this, and for that purpose you have to be careful while inserting these values, because even a small change in values will result a drastic change in the resulting value, because you know exponentials are really sensitive to change in values. Okay, so you have to be sensitive to what you are putting here. So let's see what we are gonna put here. Let's do that. Natural log of delta W by W, that is equals to h. For h we are gonna put x 6.626 multiplied by 10 to the power minus 34. Okay, that's the value of h that we are going to use. Normally we use the 6.63 multiplied by 10 to the power minus 34. So we are not going to use this one. We will use some accurate one, like instead of 3 we will write 26. Okay, so and then we have speed of light here, which is accurately 2.99792. okay, multiply by 10 to the power 8. That's the speed of light. You have to use it in order to get the result we are intended to get. And in place of lambda, I'm going to put the value of lambda, which was 500 multiplied 10 to the power minus 9. Then we have kb, which is Boltzmann constant, and its value is 1.38 multiplied by 10 to the power minus 23. And then we have temperature in Kelvin, which is 300 Kelvin. Okay, that's the calculation that we have to perform, and that's the main calculation actually. Even if you don't remember these values, like the accurate ones, you can use the approximated ones, like 3 multiplied 10 to the power 8 and 6163 multiplied 10 to the power minus 34. If you don't remember it, then you can put the approximated one and you'll get almost the true result. Okay, there is no not such a big difference, I would say, but I'm doing it the accurate way because that's my job. Okay, so let's put these values into the calculator and see what result we are gonna get. Here you can see we have got this value, and I'll be using all of the terms afterwards. It's 95.96 240541. okay, and that's the value that we have got. And let's remove that natural log, and for that purpose we I hope you understand it, that how we do that. Entire natural logarithm is actually e to the power this. Okay, 95.96240541. okay, e to the power this. Okay, and you can understand this thing, that how we can write it equals to this, like natural log of e is equals to 1. okay, you can confirm it on calculator as well. That I'll do it later because there is this value and I don't want to lose it. So natural log of e could be written here on the right hand side of this value, because natural log of e is 1 and 1 is everywhere being multiplied and divided. So it's the property of of logarithms, that anything that is the coefficient of natural logarithm could be written on the power. okay, so we can write this thing on the power of e. So we have natural log here, natural log of e to the power this, and natural log here. Now this natural log and this natural log cancels out, and we are left with delta W by W equals e to the power this thing. Okay, let me calculate what this is on calculator. So we have shift natural log answer, and it's 4.74 multiplied 10 to the power 41. 4.74 multiplied 10 to the power 41. Okay, that's the relative increase in the number of accessible states, and that's the result. I hope you got it, and we'll meet you in next one. Till then, take care and goodbye. If you have any questions, you can ask me in comment section. And if you're looking for other problems, then you can check out the playlist Statistical Mechanics, where you can find ton of problems from this book from various chapters. And there are derivation videos, step-by-step derivations and explanations that you will never find anywhere else. And even if you have any difficulty in finding out your desired video, then you can simply comment. I'll guide you to your dream video. Okay, so take care. Goodbye.